Hello and welcome, coming to you again, once again, not quite live from One Take Studios, because one take is all we have time for in life sometimes. Today's topic is additional properties of binomial distributions. So this is not an introduction to binomial probabilities and distributions, but this is an add-on to a previous video that I've actually done. Alright, so our main focus for a lot of today is actually going to be, graphing. If we're going to graph a binomial distribution, this is a type of probability distribution, and so it sort of makes sense that we're going to use a histogram. We used a histogram when we were putting together relative frequencies. We used a histogram when we were using probability distributions, so we're just going to continue down that path with some slight alterations here. Alright, so thing one, on the x-axis, what are we going to have? These are going to be the R values, alright? Point number one, there we go. The R values are going to go on the x-axis. As a reminder, in case you don't remember, R values, that is the number of successes. So the R is the number of successes for the x-axis. On the y-axis is our frequency, or in this case, our probability. So how likely is it that each of these numbers is going to be successful? So that's going to be our y-axis. And then our bar width. If you remember, for a histogram, the bars are right smack dab next to each other. So we're going to take the R values plus or minus a half just to kind of bump out those values and close up the gap between the bars. So if we keep those things in mind, we should be able to make a pretty decent looking graph. And I'd like to walk you through an example of that. Setup. We have Jim. Jim makes 50% of his shot attempts in basketball. If he shoots the ball 6 times, show the probability of 0, 1, 2, 3, 4, 5, or 6 successes. Alright, so kind of piecing this together here, R is the number of successes. Well, that could be 0, or 1, or 2, or 3, or 4, or 5, or 6. So these are all the different R values that will be on the x-axis. We don't have the probability for each of these yet, so we're going to have to work on finding that, and then we're going to bump each of these values out by a half point each direction to really get the width of our bars. Side note, his name is Jim in basketball because you shoot baskets in a gym. Haha. Okay, wasn't actually that funny. Alright, now, what comes next? Well, like I said, if we're going to graph this, we really need to know what the probabilities are going to be, and right now we don't have that knowledge. So think of this kind of like a very strange XY chart. It's not an XY chart in terms of graphing points, but again, in terms of figuring out the heights and the probabilities then for our bars in our histogram. So if we slide down first, our first R value is 0. We'd like to know what is the probability that if he usually makes 50% of his shots and he shoots 6, what's the probability that he misses all 6 of them, that he makes 0 of them? Well, PDF, this is a single probability and it is binomial, either he makes it or he doesn't. There are 6 shots total. There's our probability of success at 50%, and we're looking for the probability of 0 to make that happen. So if we jump over to our other screen here and we take a look at our calculator stuff, this one right here, boom, there we go. Alright, we are in just a regular calculation screen. Everything fun and exciting, always in the menu. What looks good off the menu today? Well, we are still talking about probability, so we probably want to go there. And this is a distribution, so we still want to go there. And we are dealing with binomial stuff, and we said specifically PDF because this is a single probability that we are trying to calculate at the moment. There are 6 trials. There are 50%, there is 50% chance of success, and we are looking at the probability of 0 successes. So what does that bring up for us? A relatively low probability. So we are talking someplace in the ballpark of 1.5%. If I round this, actually, I'm going to call it 0. I'm going to do 0.16, I think. Let's do that. 0.016 is the probability. And I'm going to go ahead and record that because I need to keep track of these, because if I'm going to graph it, I need to know again what the probabilities are, so of my R values, so that I can put that on my Y-axis. Jumping back over here one more time. Is there a faster way than running all of these individually? Well, yes. I had mentioned before that if we jump back up and just hit enter, we can now go in and edit rather than having to go all the way back through the menus. So now say I'd like to do 1 success, and there's our probability for there. So I'm going to record that at approximately 0.094094 is our probability for that one. If you remember, there was a way I said that we can do a shortcut for all of these. Let's see if we can make it happen this way. Otherwise, I'll go through a different menu, but I think we can make this happen. All right, so if we choose this, and what if we just don't put anything on the end? Ah, there it is, there it is. Remember we said that we leave that last one blank. If we leave the number of successes blank, it's going to give us a set of all of the probabilities. And so here's that first one. You see that the number matches 0.156, boom, there we go. 0.09375, there we go. So what is this next number in the list? This next number is going to be the probability for, oh, where'd it go? Yeah, there we go. 2 successes. So that's going to be 0.234. And then we go for 3 successes, and that is 0.313 if we are rounding, 0.313. And we can just go on down the line to pick these up. So next guy right there, probability for 4 successful shots, 0.234. You might be noticing something in the numbers here. If not, I'll show it to you in a second. Continue for 5 successes. We are talking 0.094, and all the way on the end then, for 6 successes, we are back to 0.016. All right, and so we can use the calculator to pick up all of our probabilities, so that when we go back to, right there, there we go. We have all of these recorded. All right, so I just grabbed all of these off of the calculator screen. The probability for 0 successes, 1 success, 2 success. All right, did you notice the symmetry that we have here? This is not typical. But why did it occur? What's our probability of success? 50%, right smack dab in the middle, which means what we're seeing is right smack dab in the middle, there's our highest, and everything scales down from there. So while this may not be common, it can happen, particularly if your rate of success is 50%. All right, so now we got to try to create a graph out of this thing. And so here's the graph I've got started for us. Notice on my x-axis, I have 1, 2, 3, 4, 5, 6, 7 spots. Why do I have 7 spots if there are only 6 trials? Notice that we can have 0 successes. That's a 7th number. So this is going to be 0, 1, 2, 3, 4, 5, or 6, the number of successes. Up the side here, I've got this sectioned off in 3 parts. My largest value is a smidge over 30%, so I will probably just call this 0.1 and 0.2 and 0.3. Again, these are percents, all right, so this is our probability. And I might actually take a moment. I'm going to do that. All right, so this is the number of successes on the x-axis. And this is the probability. Okay, so the first one is less than 2%. If that's 10%, how do I do this? Well, halfway between here and here, I want to set this up to be 2%, which is going to be something kind of short. I want it to be less than a quarter of that space if I can possibly get it. There we go. There's my first bar. Notice I went from negative 0.5 to positive 0.5. All right, that's that plus or minus 1/2 to get my bar width. For 1 success, that is really, really, really darn close to 10%, so I want to be maybe just a smidge under 10%. And again, I'm going a 1/2 point each direction, closing in the gaps between these. We're talking the next one is 23%, so right about, I want it to be under 1/2, something like that. Notice I kind of like to set my bar height and then do these. To me, it's important to have the accuracy of that top location. For 3 successes, that's going to be a smidge over 30%. So there, approximately. Pull it down, there we go. And everything else, again, we're going to see is symmetrical. Coming off the sides, just below 10%, and finishing up at something real short to the end. There it is. That's my probability distribution. Why is it highest in the middle? Well, just think about this. You're going to shoot 6, or Jim is going to shoot 6 in the gym. If he usually makes 50%, what would you expect him to make out of 6? You would think that it's very likely that he would make 50% or half, and that's where we see our largest probability is halfway through at 3 shots is the most likely option. All of the other things could happen, but 3 shots, 3 made shots is the most likely probability. All right, so up next, we're almost done. Up next we have, let's see here, let me pull this up. All right, something that you should be aware of. If they're asking you to describe your graph, we have been in places before where we looked at this and said, well, this is mound-shaped symmetrical. And to me, that makes total sense. If we're describing the graph, it's still mound-shaped symmetrical. I like that. But if we are working with binomial stuff, they are asking for the mean and standard deviation. This is how they would expect you to describe this graph. So if you were to say it's mound-shaped symmetrical, it's not quite good enough. So we are talking the mean, mu, and the standard deviation, sigma. So if we're going to describe it, we're going to need those 2 values. All right, mean is still going to be known as the expected value, which we saw for probability distributions or weighted averages. All right, so we're still, if you hear those words, that's just referring to the mean. And we have 2 new formulas. Dun, 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 dun. Ladies and gentlemen, if you're going to find the mean, the expected value, that's mu, equals n times p. That's lowercase p. That's the probability of success. I will come back to that in a moment. And here is our other formula for today, which is sigma. All right, this is our standard deviation, which can be calculated by finding the square root of n times p times q. So the number of trials times the probability of success times the probability of failure. I actually just referenced this over here a moment ago. I said, what would you expect to happen? Ooh, I used the word expect. Did that even actually trigger anything in your brain? Because that's what I was asking for, the expected value. So for the problem that we just did, we said that there are a total of 6 trials, and the probability for success is 50%. So what happens if I do 6 times 0.5? That's going to be 3. So for the example that we just did, it has a mean of 3. So if we were describing this, we would say, hey, this distribution, to describe it, has a mean of 3. I have not yet referenced standard deviation, however. So let's look at this in light of our most recent example. We're talking the square root of, let's see, n is still going to be 6, and probability of success is 0.5, which means probability of failure should also be 0.5, right? Because that should be everything that happens, 0.5 and 0.5. And ooh, did I not calculate this? Let me jump back real quick. Jumping to the screen. There we go. We need the square root of... Why do you not like me? Sorry. The square root. There we go. The square root of 6 times 0.5 times 0.5. Can I just do 0.5 squared? Are you okay with that? Hopefully you're okay with that, because that's what 0.5 times 0.5 is. And we get a value of approximately 1.22. All right, so 1.22, that would be, jumping, right here, that's going to be our standard deviation is 1.22. So in this example, if you said, hey, could you describe this graph for me? Can you describe the distribution of these probabilities? I would say yes, I can describe that. It has a mean of 3, which you can easily see by the tallest bar there, and it's got a standard deviation of 1.22. Great, lovely, okay. Now, something that we have referenced also before, Chebyshev. All right, Chebyshev's work with how many standard deviations things are away from the mean is come back into play again, and we can now determine from this that it's really unusual for the number of successes to be higher than mu plus 2.5 standard deviations or lower than mu minus 2.5 standard deviations. Now, again, if you're not thinking, you just look at this and it looks like Greek, and part of it is Greek. But think about this. Again, just think about it in light of what we're talking about over here. We are saying that the mean for this set of data is 3. So what happens if I do 3 plus 2.5 standard deviations, so plus 2.5 times 1.22. Okay, what is that going to be? Let's see. So we are talking 3 plus, why? There we go. Oh, it's a rough day. 3 plus 2.5 times 1.22. So the mean, 3, plus 2.5 standard deviations. That means on the high end, that's going to be 6.05. And while I've got this screen, I'm going to go ahead and go back and recalculate this at the low end, and then we'll discuss what the numbers mean. So I want the same thing for the other direction, but I'm talking about going 2.5 standard deviations below 3 this time instead of above, which gives us a delightful, let's see, jotting a couple things down here, there we go, is going to be negative 0.05. All right, what does this mean in terms of what we just did? Jumping back one more time to my screen. There we are. Okay, so think about this. This statement says that it's not likely that we're going to have more than 6 successes. Duh. That makes total sense. There were only 6 shots to begin with, so what's the probability that I'm going to have more than 6 successes? Yeah, no, not happening. And it is unusual for the number of successes to be lower than mu minus 2.5 standard deviations. Here we go. Again, we're not going to have a negative number of successes. So we can see this happening very clearly here, that if we do this calculation, we would expect most of our successes to be within that range and not outside of it, which, by the way, is going to be a new calculation for outliers. Dun, 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 dun. If you are more than 2.5 standard deviations from the mean, it is rare, it is unlikely, and it is one of the ways of defining outliers. All right, so that is kind of pulling everything together. Again, that's just a takeoff on the previous conversations for binomial stuff, and we can make graphs, and yeah, keep striving to understand things, watch out for the details, everything should be good. Thanks, guys.